Hi. So till now we have seen that the notion of time complexity really means the counting the number of instructions that a program is executing. Since the count of exact number of instructions that a program is executing is difficult, we have introduced something called order notation, which helps us count the number of instructions that a program executes. So there are three kind of notation that are defined in order notation. There is something called big O, there is something called omega, and then a theta. So there is a big O of some f of n, there is a theta of f of n, and there is something called omega of f of n. Okay. So these are three different kind of order notation that are possible. There are some other as well, something called small o and smaller omega, but these are the main three prevalent that are asked generally. So what does this big O mean? And this is the one that you would be seeing often. So big O means that whatever your complexity is, let's suppose your exact complexity is some g of n, right? Some function of n. Now big O of fn in some terms mean that as you go towards infinity, fn is some constant times fn is greater than or equal to g of n. So if I go ahead and plot that in a graph, so suppose there is some graph that is g of n. What this means is that there is some function c times f of n. So there is some function c times f of n, which after certain point, let's call that some x0, for every x greater than x0, c times f of n is greater than equal to g of n. So this is what this big O means. So a program is big O of n square. That means asymptotically n square is more than the actual complexity of the program, or almost same. Like there is an equal to over here, but either it's the same or it's above that. Okay. So let's say there is a program which is taking n square plus n number of steps. So this is order n square, right? Because you can take 2 times n square, right? For this n square, you can take c equal to 2, and beyond say n equal to 10, everything is, this function is bigger than this function, right? So this is definitely order n square. This is also order n cube, right? This is also order n cube, because we can say that it's n cube because you can also define n cube simply as the f of n, and you will see that after some value like 10 or 20, n cube will always be greater than this function, right? So in that case we say that it is also order n cube. So you generally try to mention the most tight bound, like it's something like whatever code I've written, the number of instruction will definitely be less than equal to n square number of times, something like that. Whenever you say that my program is order n square, you basically mean that my program would take less than equal to n square c times n square number of instructions. That's what you are saying. Okay. So you should generally try to give out the most tight order notation for any program, because that will help you, right? If you just say that my program is n cube, that's not giving you a lot of useful information, even though it's n square, right? So if it's n cube, it is taking longer time. So you would like to have as much upper bound on the function of your number of instruction as good as you want, right? As good can you have. So you'd better report that as order n square, right? So this is what this order big O notation means. Now let's quickly talk about the other two. So apart from this big O, there are two other, right? Theta and this weird omega. So let's talk about what these two mean. Now, when you say a function is theta, that means, suppose this is your function. Okay. So we say that a function is theta of fn. So let me write that. So g of n is equal to theta of f of n if this is c1 times f of n, this is c2 times f of n. So just by changing the constant, you can make, so suppose this is x0, beyond x0 towards the infinity, you can make fn go above this g of n that you have, that is your actual uh, complexity or your actual number of instruction that you need. So you can shift fn above gn by just changing the constant. So if it's just about constant, then you say it's theta, right? So it's like saying it's exactly equal to fn without the constants and the lower order terms. Okay, that's what you mean. For omega, it's just a lower bound. So you have some function over here. If some function beyond some point is always less than this, like if you take, let's take an example. If you take order, eh, if you take order n square, so this means this is less than equal to n square for sure. If you say it's order n square, this basically means it's always greater than equal to n square. So if my complexity is something like let's say n cube plus n square, so this is always greater than equal to n square beyond some point, right? So we can say this is order is omega n squared, and this is theta of n cube, because if you take just n cube, this is always less than equal to this function, right? And if you take 2n cube, beyond some point this will be always bigger than this, right? So this is called theta notation, right? So these are the other two notation that we have, the theta and omega notation. So these are too many technical terms over here that you have c1 c2 x0 such that this condition follow. These are the theoretical stuff. If you have to remember this, you just need to understand that this big O over here is actually giving you, big O is your upper bound, lower bound, omega is your lower bound, and your theta is exact class, or you can say you can make it sandwiched between the two type of functions of the same type, okay, just by varying the constant. So if you have some function like n to the power c times some with a coefficient a plus some b times some lower order terms, by lower order means like the power is less, so this is order nc n to the power c, this is also equal to order n to the power c. So this is also not exactly equal to, this is also order in the set of order n to the power c plus 1 and so on, everything beyond that. Because when we say that this order, this basically represent a set of functions, right? Every function that is less than equal to this by the definitions that we discussed earlier will be in this class, and this function is also inside this class. So these order notations are actually describing a set of functions that are valid, and these functions would be present in these sets. So which all sets it is present in? Everything beyond n to the power c. So n to the power c, n to the power c plus 1 and so on. Everything in each and every one of those sets, this function will be present, right? Again, if you have this, if you talk about omega, that's just n to the power c, then n to the power c minus 1, because it has to be sandwiched. No, sorry, it's not sandwich. For omega you just need to have lower bound, so omega of nc is all functions greater than equal to nc by the highest order term. For this also it's greater than equal to nc plus 1, so nc minus 1. So that's also true, right? Because the higher order term over here is something like this, right? Is greater than this. So this is also true. But in theta, if you think of just polynomial functions, this is exactly theta of n to the power c. That's it, right? So with that, we have the three formal definitions. So most of the time people generally talk about theta, but they are saying big O. So these are the actual definitions. So sometime if you are confused, go with the actual definitions. But in most of the cases, when you are asked time complexity, you say big O of the tightmost upper bound, that is like theta. Okay. So you basically tell out the theta in by the name of big O. Okay. So in most of the cases, you will be saying big O of n to the power c, whereas it actually should be theta of n to the power c. But again, this theta is only works when you also have a lower bound of n to the power c. But so that's why we talk about order notation in most of the cases as big O. So you would be seeing big O all the time, and we would be comparing things using big O only. Because once there is an upper bound, we know that it will not go beyond some limit, and that's where our time limit will lie, right? So these are the terms or order notation classes or sets, and using that you need to find out what is my algorithm and which set my algorithm will lie in. Okay, so these are all theory, right? Let's quickly look at some examples, how like these are all like standard theoretical stuff. How do I look into code and tell out the time complexity of the code? So let's suppose you have something like this: I equal to 1, I is less than equal to, let's take 2 into n plus 7 I plus plus, and you do some constant work like one or two number of instructions. Like let's suppose you do 3 instructions here. Okay, so there are, even if there are x number of instructions, if there are very small number of instructions, we can call that order 1, right? Order 1 means there are constant number of instructions. Order n means it depends on n, it's bounded by n. Order n square means it's bounded by n square, right? So if there are very few number of instructions, you can call them order 1. Okay, so we say that there are order 1 number of instructions in this for loop. So what is the time complexity of this? So if you think about this, this loop will run exactly 2 into n plus 7 number of times, right? And every time it runs, it executes these 3 instructions, so it's multiplied by some 3 or some constant k, right? So this will be some constant k, 2k constant. This is also constant, since k is constant, 2k is constant, times n plus 7k, right? This is also constant. So now whenever you have some sort of this function, you just need to note what is my highest power term in this polynomial. That's n, right? So you just report this is order n. Okay, that's how you find out the complexity of any program. Okay, find out the approx number of instructions that you have, which should not vary by the obviously the leading term. You should not miss out a leading term like the highest power term, but find out the approx number of instruction and just tell out the highest power term in the polynomial expression that you have. It might not be exactly polynomial, but again, whatever you have, just tell out the fastest growing function in over there. Okay, so we'll be looking at those examples soon, so don't worry about that. Let's look at one more example. Okay, let's say you have for I equal to 0, I is less than n, I plus plus, again an n, for you are not writing data types over here. So j equal to 0, j is less than n, let's take j plus plus. Okay, and then this loop, this loop, this loop ends. There is some order 1, I mean constant, right? Because we know that multiplying by a constant doesn't change anything, right? That doesn't change the polynomial. So we just multiplied by 1. Why not 1, right? So this is just order 1 work. And then there is another loop after this sequentially, right? For integer I equal to 0, I is less than 2 into n plus 5, I plus plus, right? So, and again order 1 work, some order 1 work, okay? Now this is the code that we have right now. So for this code, you have two separate portion, right? This portion executes and then this portion executes, right? So how do we find out the time complexity for this? Now the rule is when you go inside nesting. So nesting means multiply, okay? Because if for every number of times this runs, this also runs that many number of times, it's just multiplication, right? The number of times this order 1 work happens. So if there is a nesting, you tend to do things like a multiply operation. It might not be exactly multiplication, this thing might depend on exactly this one, but again in general such loops it's mostly multiplication, okay? Again when you come to this part, this is very simple. This is just a simple order 1 work inside a loop. So this will work simply like the previous example, but now we have this part running and then after this part is running. So when you have sequence, then you do addition, because this will run and then this will run. So these two are not dependent, right? So this much time plus this much time, that's it, right? So for that, now you can simply resort to finding out the term complexities in this way. This is order n, this is order 1. So this loop will take order n, right? Okay, and since this loop is taking order n, and this order n work will be done n number of times, this bigger loop will take order n square, right? Simply this one is 2 into n plus 5, but that's linear, right? You don't bother about the constants. So this is order n, and now you add, so order n square plus order n will be order n square. Why? Because this is dominating, right? There is a polynomial which is working in n square, and there is a polynomial which is working which has a leading term in n. If you add them, you get a polynomial in order with the leading term with order n square. So this is your final complexity, right? So this is how you look at codes and try to find out the complexity of this, right? Let's look at one more example. Okay, so let's look at if there are more than one inputs into the problem. So for I 1 to n, okay, so I'm writing this shorthand notation for loop. So this is exactly for I equal to 1, I is less than equal to n, I plus plus, right? For j 1 to n, okay, then there is some order 1 work that's being done over here, and this loop start, this loops end, this loop start, this loops end, okay, and then again another loop starts. So let's say I goes from 1 to n, okay, and this loop starts for I goes from 1 to m. There is another variable m, let's say, okay. So the algorithm can take multiple inputs, right? There is an input n, there is an input m. So how do we find complexity in this case? Then there is another order 1 work done over here, then these two close. So how do we find the complexity for these? So again there are two sequential parts, so we try to find out complexity using breaking up this part into two other parts and then finding each of them individually, and for each of them it's nesting, so you have some sort of multiplication. So let's look at that. This part is order n, right? This order 1 term work is being done order n number of times irrespective of I, so this is order n, and then this work is being done n number of times, so this part is order n square, right? This is order n square. Now this part is order m, right? And this part is order n times m, because order m work will be done n times. So this is n into m times, right? Now there's a weird scenario over here that you have n square and n into m. How do you add that, right? Like you have, now your final complexity will be nothing but order n square plus n into m, right? This is something like what we are doing over here. So it will be some constant times this plus lower order terms, constant times this plus lower order terms. So you can write the sum of these two in this form, or also you can write order of n times n plus n. Okay. So if there are multiple variables as input, you will have multiple variables in the time complexity as well. Okay. So this is how you look at time complexity of codes, and this is very essential to understand, as whenever you write a code, you should be clear about its time complexity before even writing it. What's the point in writing a code that won't get past the time limit? Okay. So when you're thinking about a problem, make sure you first go and think about the time complexity of the code, and then you decide on whether my time complexity that I have, like whether my algorithm that I've designed has a time complexity that will pass the time limit. If yes, then I will code the solution. If not, then don't code the solution. There is no point in coding a solution that won't pass. You only get points for things that get passed, right? Obviously you can practice out things writing suboptimal solutions, but again, when you are solving it in contest or in some test or somewhere, you don't really want to solve problems just for fun, right? You need to get the score out of it. So now you know almost how to find out the order notation of any code that is given to you, right? now Now you have the order notation. Now how do you decide whether this order notation, whatever the order of your code is, whatever the time complexity of your code is, whether that will pass the time limit or not? How do you decide on that? That's also not that trivial, right? Like you have a order notation with you, but how do you decide on whether that will pass the time limit? So let's look into that first. So there is a quick thumb of rule that you can follow in most of the scenario. Okay, so you will get something of the form f of n comma m so on, right? Some polynomial, something like this in most of the cases. So let's take an example. Okay, let's take, you get something like order n square. Okay, and your problem will define the bound of n. Okay, so in the problem you will be given constraints in most of the cases. If there are not, you just tell that my complexity is this, can I reduce better than that or not? But if you have a bound, you will be given something like 10 to the power 5. Okay, so n is less than or equal to 10 to the power 5. Now whether something like this will pass my time, will pass the time limit or not. Let's suppose time limit is exactly equal to 1 second in some OJ. Okay, OJ means online church. So keep a rule of thumb that whatever the value of n is given, take the maximum value that it can attain, put it into n squared. Okay, so you will get 10 to the power 10, right? If you put 10 to the power 5 in n squared, you get 10 to the power 10. See that if this is less than or equal to 10 to the power 8, you can code the solution in most of the cases. Just to be safe, if it is less than or equal to 10 to the power 7, like you are even safer. Like this will, if your complexity is less than or equal to this, it will certainly pass in most of the cases. And even sometimes things less than or equal to 10 to the power 8 passes. So even if you have a complexity that is of order 10 to the power 8, it might pass. Less than or equal to 10 to the power 5 into 10 to the power 7 passes for sure. Like make sure that this passes. But if you go something beyond 10 to the power 9, okay, so if you're whatever you, after putting the value, if you get something greater than or equal to 10 to the power 9, okay, it will not pass. Mostly it will not pass. So 1 second can handle something of order 10 to the power 9 number of instructions, and you cannot pass. in most of the cases, why we take these numbers even though they can handle 10 to the power 9, because there are some constants, right, that we dropped off while we are formulating the order notation. So if you drop off the constants, there might be some extra multipliers over there. So that's why most of the cases, if there is such a order notation which gives you 10 to the power 8 or 500 to the power 7, that is safe and you can code the solution. But in general, you should not be coding anything greater than 10 to the power 9. There is no point in coding a solution that won't pass. Okay, so now let's quickly have a look at some constraints that will pass. Okay, so in a problem, let's suppose you are given n is less than equal to 10. Okay, so you can code something like a solution that takes n factorial number of times, like something like generating every permutation, or something like order n to the power 7, because if you put 10 into 7, it's 10 to the power 7, right? That will pass easily, right? Or order something like let's say n to the power 6. So if these are the complexities of your solution, this will pass provided n is less than equal to this, right? If n is less than equal to 20, you have order, you can even code solutions like 2 to the power n multiplied by n, order n to the power 5, because if you put 20, you will see that this is within our range. If n is less than equal to 80, order n to the power 4 should be sufficient. Yeah, if your n is less than equal to 400, order n cube is sufficient. If n is less than equal to like 7500, even then order n square works. Okay, so how are we formulating these? Whether a code with this complexity will pass or not? Just put in these value and check whether that's less than equal to 10 to the power 8 or 10 to the power 5 plus 7. First 10 to the power 5, 10 to the power 7 multiplied by 5, 500 to the power 7, right? That's the bound, that many number of instructions. So just put the value of n and understand whether that will pass or not. Okay, and similarly, if we go ahead and try to write some more possible expressions, if n is less than equal to say 10 to the power 5, these days order n square root of n passes most of the cases. If n is less than equal to 5 into 10 to the power 5, order n log n is safe. If n is less than equal to say 5 into 10 to the power 6, you should try to code things that are just linear or order n. Okay, if n is less than equal to 10 to the power 12, okay, that's weird, like how would we be able to do this? So it need not be exactly polynomial, right? There are logs, root n, so you can code something like root n log n, something like this, or even order root n passes, right? Something like these things passes in such solutions. And if n is less than equal to 10 to the power 18, you need to code something like order log n or log square n, something like this, order log n, or order 1, order log n, right? So these are the typical algorithm complexities that will pass given these constraints in the question. So you need to understand these very well, that whenever you have some n value and you think of some solution idea, try to think of the algorithms complexity when you are thinking about the idea itself without coding. You don't need the code to think about the complexity, right? So when you are thinking about the problem, you will be able to understand that, okay, I will loop through, like I will need two loops to find out something, and then I will do these two loops. So you will be able to virtually calculate the time complexity of it in mind or in copy if you need. But after you have computed the complexity, don't forget to put in the values of maximum and m, or whatever makes your complexity worst. Put them into the expression, find out the time number of instructions or the value that's coming out of this order notations polynomial, and if that's less than equal to 10 to the power 8, you're good to go. Even it's better if it's less than 10 to the power, like 10 to the power 7 into 5. Okay, and these are some standard order notation complexities for some algorithms. So if this is the constraint, these kind of algorithms which follow these order notations will pass the time limit there. So these are all about the order notation. So that's all for this video. Thank you.